Hello, it's Stat135, Lecture 22. Last time you had a midterm, great effort, and most of you found it hard. Some of you found it very easy, and I envy you. Well, so this is going to be a great weekend because you have nothing going on next weekend, so enjoy. Some post-midterm topics. We're going to do parametric paired two-sample t-test today, and chi-squared tests next week, followed by non-parametric two-sample t-tests, followed by analysis of variance, regression, both simple and multiple, as well as Bayesian statistics. So today we're going to do paired two-sample t-test. We'll see how to do paired and unpaired tests in R, and we'll do some preliminary stuff on multinomial distribution and chi-square test. So, section 11.3, comparing paired samples. So we wish to estimate the difference in the population means of two populations, X and Y, but where X and Y are correlated, there's a pairing between Xi and Yi. So we can no longer assume that our samples are coming from independent populations. So X1 to Xn, Y1 to Yn, same sample size. And we think of Xi, Yi as a pair, IID. So the covariance of Xi, Yj is 0 for I not equal to j. And the variance of Xi, Yi, this is what I'll call sigma xy, and that's the correlation coefficient of x and y times the standard deviation of x times the standard deviation of y. Di, let's let that be the difference of xi and yi. Then the expectation of di is mu x minus mu y, and the variance of di is the variance of xi minus yi, and that is sigma squared x plus sigma squared y minus twice the covariance of x and y. And for large N, d, the sample mean, x d bar, this is approximately normal. And that just follows from the CLT, since each of the DIs are IID, and D bar then is normal mean mu x minus mu y and variance as written here. So notice that if x and y are positively correlated, then the variance of D bar is less than what the variance would be if x and y were uncorrelated. And so this says that the paired case is more efficient, and this means that the standard error for D bar will be smaller than the standard error for x bar minus y bar if x and y are unpaired, are uncorrelated. And this means that you're more likely to reject the null for the paired data, right? Because your test statistic will be larger. And, well, this is good if the alternative is true. It's bad if the alternative is false. So now let's talk about paired t-tests. So now the DI is normal, and generally sigma squared is unknown, so our test statistic is comes from a t distribution with n minus 1 degrees of freedom. And by duality of hypothesis testing and confidence intervals, we reject when the absolute value of D bar is greater than t to n minus 1 degrees of freedom alpha over 2 the standard error for d bar, or equivalently we would reject if the population parameter is not in your confidence interval. So next we did an in-class exercise on B courses where I showed you the code to do paired and unpaired two sample t-tests in R. And so I just made up some data here, and I did some data cleaning by making my data frame tidy using the gather function. I examined the box plot here. It looks like the medians are different here, so likely the means are different. It also looks like the standard deviations are different. I look at a QQ norm plot to see whether my data is approximately normal, and it should fall along a straight line, but that doesn't look so good for the x's here. But and also the SD, I calculate that and they appear different. So based on this, I probably would not do a parametric test. I would do a non-parametric test called a Mann-Whitney test that we'll do soon. But since we don't know about non-parametric tests yet, let's just do both an unpaired and a paired test and see what difference we have. So first we'll do a unpaired test. The SDs are different, so our degrees of freedom formula on page 428 I calculate here in R, so you can see how I do that and copy that in your own code. There turns out there are 15 degrees of freedom. Let's let alpha be 0.01. We get a test statistic of 3 and a p-value less than 0.01, so we reject the null. Now, if we treat our data as being paired, then like in a before-after study, then we see that we get a larger t-value, again because the standard error is smaller, as we discussed earlier, and so our p-value will be smaller, and this is a good thing if the alternative is true, and it's a bad thing if it's not true. And here I calculated the efficiency for the paired and unpaired, and you can see it's less than 1. So finally, we just did some preliminaries for section 9.5. Let's just talk a little bit about the multinomial distribution as sort of a generalization of the binomial. So the binomial is a sum of n independent Bernoulli P1 random variables. So Bernoulli P1 random variable has two outcomes or cells. Let P1 be the probability of outcome 1, P2 the probability of outcome 2. You could call P2 just Q1 if you'd like, but anyway. In n trials, what's the chance of getting x1 outcome 1 and x2 outcome 2, where x1 plus x2 is n? So it's n choose x1, which we could also write as n choose x1, x2. So I'm just writing this so you can see how this would generalize if we had more than two outcomes. So, for example, if we have two red marbles and 7 green marbles, and we pick 3 marbles with replacement, then P1 would be 2 over 9 and P2 would be 7 over 9. So the chance that we get RRG would be P1 squared P2, and there are 3 factorial over 2 factorial 1 factorial reorderings of this. So there we are. Now, In n trials, you could write your results as making an observation table and an expected table. So our observations are x1 and x2, where x1 plus x2 is n, and what we expect is np1 and np2. So now the chi-squared statistic is the sum over all the cells. We have two cells in this case, where we take OI minus EI squared over EI. So this test statistic I'm going to show is, as n goes to infinity, a chi squared with 1 degree of freedom. So 1 less than the number of cells. So in the case where we have two trials, as I said, we're summing two things here, and I've written out what these two things are. And if you do some algebra, you'll see that we get x1 minus np1 squared over np1q1. Actually, I'll write here p2. Well, I'll just write q1, fine. So that's the standard deviation. So this is approximately normal squared. That's the variance. So this is approximately normal squared, which is chi squared with 1 degree of freedom. So, and that's right. So binomial np1 is approximately normal np1 and p1q1. So the cool thing here is that I'm writing a sum of two terms here, but these terms are dependent. Right, and this dependency here is eliminated by doing this algebra, in which case we just get a single term. So more generally, we'll have, let's say, m terms here, but there'll be there'll be a dependency between them. So there'll be a dependency between them, and it's to see what the algebra manipulation you have to make to get it to be a chi squared with m minus 1 degrees of freedom is hard. So I just did it here in a simple case so you can kind of see what's going on algebraically. So we'll do this next time in the multinomial case where we have more than two outcomes, and show that the chi-square test statistic is it's approximately chi squared with the number of cells minus 1. So have a great weekend, well deserved, and I'll see you next time.